I'm going to start the recording. Laughs on Wednesday morning. um, so suspenseful. uh, Welcome to Structural Analysis. We are in lecture 13. We're going to continue our discussion on shear and moment diagrams. I thought I had updated these because maybe I'm pulling an older file from my Surface, because we graded homework 4.1 and the solution's already up. But I'll check that. But yeah, the grades to that are posted. Homework 4.2 is due today. That's your first shear and moment, like I'd say the first shear and moment diagram assignment. And then today we're going to have another shear and moment diagram assignment, although we're going to extend our graphical approach by looking at distributed loads and not concentrated. Well, we're going to have a problem that has concentrated loads, but really the star of the show is the distributed load. Let's just hop right into it. So I want to make sure that we keep emphasizing these relationships, because whether we're talking about concentrated loads or distributed loads or whatever, the relationship still holds true. That if I have my load diagram or my free body diagram and I integrate it, I get the shear diagram. And then if I take the shear diagram and I integrate it again, I get the moment diagram. And then, you know, the inverse works as well, right? I mean, what's the derivative of moment? It is shear. What's the derivative of shear? It is the load. And so if the integration relates to the areas under the curve, then we then draw the next diagram, we can look backwards and make sure that the slopes of the diagrams are matching as well. And so this relationship yields the following graphical conclusions. You know, when we look at the shape of the shear diagrams and the moment diagrams, we want to make sure that it makes sense. So if we're looking between the load diagram and the shear diagram, we know that at a given point, the slope of the shear diagram is equal to whatever the load is. And then between 2 points, the change in shear is equal to the magnitude of load. And the same thing can be said between shear and moment. So at a given point, the slope of the moment diagram equals the shear diagram, and then between 2 points, the change in moments is equal to the area of the shear diagram. Now remember, our derivation was actually focused on distributed loads. When we started our problems, we didn't even start with distributed loads. We started with concentrated loads. We do that because the geometry is maybe a bit simpler with concentrated loads, but since our derivation was focused on distributed loads, let's actually start testing it and looking at distributed loads. Now, what's the deal with the distributed load? Okay, so in the case of a distributed load, the load is constant between 2 points. See, for point loads, in between the point loads, the load is 0. Well, between 2 points under a distributed load, the load is a constant, and so we follow that integral relationship. Okay, so if I have a constant load going down, as I have here in the image, that is a negative load, right? So when I integrate that, the slope of the shear diagram is linear, and it is negative because the load is negative, so that's why I have the shear diagram going down, okay? And then if I further investigate that shear diagram, what do I find? Well, on the left side of that shear diagram, I have a high shear value, and on the right side of that diagram, here, I'll start using my pointer. On the left side of that shear diagram, I have a high shear value. On the right side of that shear diagram, I have a low shear value. And so that relates to the slope. When we're in person, and I might even say this when we start doing our examples, I usually use the terms lot to a little. So over here on the left, I got a lot of shear. So a lot of shear means a lot of slope on the moment diagram. So a high slope. So a lot of slope. And then over here on the right, a little shear, a little slope. So a lot to a little. So that's why I have the diagram sort of drawn from a lot of slope to a little slope. Like it starts off really steep and then it kind of gets flatter as we progress to the right. And as for the math, if the shear diagram is a line, is a linear expression, then the moment diagram is going to be quadratic. I mean, think, if I take the integral of like x, what do I get? I get x squared. I mean, x squared over 2. But the idea is if I have a function that's a line and I integrate that, I'm going to get a quadratic expression. And so that's why your moment diagrams under distributed loads look like parabolas, okay? Another thing to point out, when we integrate the shear diagram, we're again calculating the area under the curve, and the graphical approach is still going to work, because before, when we looked at concentrated loads, we just had rectangles, like it was just the area of a rectangle. Now we have the areas of triangles. Well, if you can calculate the area of a triangle by hand, you don't need to break out the integral to do that. If area is A, then what it means is if between these 2 points, the change in your moment is A, the area under the curve. Just remember, integration, we're just the area under the curve. Now, I want to show you something that's going to happen with distributed loads that you kind of need to be aware of, and it's a little bit of a geometry problem. So stuff like this will happen with moment or with shear diagrams, and so I want to sort of remove the mystery a bit. So I've got this region, let's say, in a shear diagram, and I made up these numbers. These numbers don't really matter all that much. And so let's say I have a shear diagram that goes from 25 to like -75. Okay, well, in order to draw the moment diagram, I have to find out the area under the curve. So what it means is I have to find the area of these 2 triangles. And so I want to make sure that we're clear on doing that easily. I have been teaching this class for a long time, and I found that it's not the hard stuff that trips people up, it's the easy stuff. So how do we find the area of these 2 triangles? So I have that here drawn here on the board. So let's just take a look at this. So this is positive 25 kips right here, and this is 75 kips. And you could start setting up some really complicated ratios and all that stuff, but let's just keep it simple, okay? I want to find the area under these 2 triangles. The first thing I'm going to do is I'm going to compute the slope of this line, okay? And I'm going to go back to basics when we're computing that slope. If you remember from algebra or whenever you first started learning about this, the slope is the change in y over the change in x. You know, that's simple. Just change in y over change in x, okay? And so we ask ourselves, how much do we change, in each direction? So for x, we change 25 feet. And in the y direction, we go from a positive 25 to a -75. So we get a change in 100. So 100 kips. And if I wanted to be technical, I would say that's negative because we're going down. And so this would be -4 kips per foot. Now, what's even easier in shear diagram land is you often don't even need to compute that, because look at the units, right? Okay, this is kips and this is feet, so 4 kips per feet. Look at that number. That's just the load, right? So if you look at the load diagram, you can just look at that line and say, oh, the slope is -4 kips per foot, because above here there's going to be a load and it's going to be -4 kips per foot. Okay, and so now that I've got this, in order to determine the distances, it is really, really simple. If I want to determine x1, all I've got to do is I take rise over run, 25 kips, and then think rise over run, just divide that by the slope. Okay, so 25 divided by 4, what is that? Is that like 6.25? And then x2, 75 kips over 4 kips per foot. I didn't do this one in advance, so somebody help me out. 75 divided by 4, that's 37.5. What is that? 18.75. Did I do that right? Yeah, I did. I got that right. And so that's it. So this dimension here, this dimension here is 6.25 feet, and then this dimension here, 18.75 feet. And I mean, does that make sense? What is 6.25 feet plus 18.75 feet? Sum them up and you get 25. That's the total length. And so to determine the area, so area of this first region right here, just 1/2 times the base times the height, 25 kips. Area 2 1/2 times the base times the height. And then put a negative out there since that's negative. And then 0.5 times 6.25 times 25. This one comes out to like 78.125. And this one comes out to be negative, I don't know, 0.5 times 18.75 times 5. 703.125. And also look at your units, right? This dimension on the x-axis, that's feet. The y-axis, kips. These units are going to be foot kips. Foot kips. And does that make sense? Well, what is the area of the shear diagram? It's the moment diagram. These areas should have units of moment, foot kips. So that makes sense too. Okay. Does anybody have any questions about this before we get into our example? Again, I think this is a pretty straightforward geometry problem, but I don't want to get marred up by the geometry later. I kind of want to handle this stuff first so that when we start jumping into the shear diagram, it's not so bad. All right. And again, don't hesitate if you got any questions, because this is, like I said, this is going to be relevant here in a second. Okay, so I want to look at the following problem. So we're going to draw the shear and moment diagram for this beam, and I decided to not give you the reactions on this one. I actually want to keep those out because I want to do this problem from start to finish, and I also want to head off a potential conceptual error that you might have with distributed loads. So this problem we're going to do from start to finish. We're going to compute the support reactions, draw the shear diagram, draw the moment diagram, do it right, and do it all together. So does anybody have any questions? My phone is ringing. Oh, what's going on there? It's like I'm in class. That's way more important. All right, let me stop the share and pull up the notebook. Okay. All right, so let's handle this like we have handled problems in the past. So this is a little bit of a review of reaction problems. Like I said, up until now, for the past few lectures, I've sort of just assumed that, oh, you know how to do this. We've done it before. Let's go through it, okay? So we've got a point load, and then this distributed load. So I have 3 kips per foot applied over a distance of 60 feet. So I'm going to idealize that as a single distributed load. How much is that distributed load going to be? Making sure everybody's awake this Wednesday morning.
Yeah, it's going to be 180 kips, sorry.
Yep, 180 kips, exactly right. And then this dimension here, making sure everybody's with me. What is that?
30 feet.
30 feet, exactly right. Now, that is correct. And I have my unknown reactions. I just assumed those were upward. Remember, with reactions, we assume they're upwards. If we get a negative answer, it doesn't mean we need to develop significant emotional distress. It just means we assumed upward. We were incorrect. They're downward. Now, here's the point I want to make. Okay, that 180 kips, that is a construct that we created, that we idealized just to make the reactions part easier to do. Okay, when we start drawing the shear and moment diagrams, that 180 kips doesn't exist. We have to draw the shear and moment diagram for the loads as they're present on the beam. Okay, so I'm actually going to copy this image over, and I'm going to assume that that never put that 180 kips there, and you'll see what I mean here in a second. Okay, so let's handle this like we would in a reactions problem. So let's sum moments at A. All right. And so what do we got? So we're summing moments at A. We don't consider the reaction at A. We have 180 kips at a moment arm of 30 feet. And so we'll put that over here, 180 times 30. Okay, that's easy. Okay, we've got the 30 kips times a moment arm of 40 feet. We got the CY times the moment arm of 60 feet, and that's going the other way. And so just to make sure everybody's paying attention, 60 kips, might have given it away. What's the moment arm here?
$80.
There we go, 80 feet. Okay, so we do 180 times 30 plus 30 times 40 plus 60 times 80, and you should get 11,400. And then those units are foot kips, or you can do foot kips, whichever one you want to do. And then that equals CY times 60 feet. And then CY equals what? So what's 11,400 divided by 60? It is positive 190. Oh, you beat, yep, exactly right. Sorry. I stole your thunder there. I'm sorry. Okay. So now what we're going to do is we're going to sum forces in the y direction. And we've got, okay, so we've got AY going up. We don't know what that is. We've got CY going up, but we do know what that is. CY is positive 190, because we just figured that out. And then we've got 180, we've got 30, and we've got 60. Okay, so AY plus 190 is, what is that? 180 plus 30 is 210. 210 plus 60 is 270. That's 80. All right, so that's easy, and hopefully that's pretty straightforward. I'm going to give you all a second to catch up, and then we will we'll see if y'all have any questions. Which while everybody's catching up, anybody have any questions? Okay. All right. Now, like I said, now we're going to draw the shear and moment diagram, but I want to be clear here. Actually, hold on. Let me recopy this image. You don't have to do this in your notes, but I'm doing it here to make a point. Okay. This is the beam, okay, right here. Remember that 180 kips that we used before, like if you look up here, this 180 kips that we created, we did that only to make the reactions part easy to solve, okay? So when you're drawing the moment diagram, that 180 kips is gone, okay? What exists is what is on the beam, the 3 kips per foot. So it's an easy thing to start drawing your moment diagram, think, oh, I got a 180 kips, I need to drop straight down. No, that was a resultant that we put on there just to make the reactions part easier to do. Okay, so let's start drawing our shear diagram. Now remember, this was AY is 80, and this is CY is 190 kips. Okay. All right, so let's start drawing some dashed lines going downward. As for how many of these things you put on here, there's no real like rule. What I tend to do is just sort of put them on every, what I would call important point on the structure. It's like all the reactions, the beginning of the beam, the end of the beam, if there's any point loads on the beam. And sometimes you might even have more lines as you go down from your shear diagram, and you'll see that as we get here in a second. Okay, so that's good. Let's put this, I don't know, down here. Let me scroll down a bit. Let's put this here. Let's do that. That's good enough. Okay, so that's our shear diagram. So we'll say V, say that's kips, and then let's put our little tick marks on there to indicate that that is the 0 line. Okay. All right. Now, whenever we draw a shear diagram, remember the rule with equilibrium. We better start at 0 and we better end at 0, okay? Because sum of forces in the y direction has to equal 0. And so a shear diagram, again, it's sort of a graphical check that our reactions make sense. Because we got 80 and 190. That 80 and 190 better work, okay? Now, everybody that's on chat, y'all follow along because I might ask for your help throughout all this. Okay, so I start at 0. It's the first load that I see starting at the left and working my way over. So the first thing I see is this 80 kips right there. Okay, so I see 80 kips. I jump up to 80. Okay, now let's see what happens from here, okay? So this is point A. Let's see what happens from point A to point B. Now, I'm going to ask chat here for a question. Help me out. From point A to point B, how much load is present on the beam? From point A to point B. In other words, how much is this? How much is that load? 120 kips going down. You're exactly right. So if I'm at 80, okay, so let's ignore the shape of the diagram and let's just get the points down right. So if I'm at 80 and I drop down 120 kips, that's going to put me where?
It's going to put you at negative 40.
Exactly right. So that's going to be maybe about like that. That looks about right. And now what does the shape look like? Well, it's a constant load, linear shear. So this is a line. So it's going to drop like that. Okay, and so that's my shear diagram for this region. Okay, and so there's some things to talk about with what happened here and how that affects our moment diagram, but for now, let's not worry about that. Okay, so this is negative 40. Okay, so I'm at negative 40. Then what do I do? What do I see at point B? I see a 30 kip load dropping down. So a 30 kip load going down. If I'm at 40, I drop down. What does that put me at? Puts me at negative 70. This is negative 70. Oh, I didn't mean to do that. I think my first one was prettier, but we're just going to go with it. Okay, so I'm at negative 40, and I drop down, I'm at negative 70. Okay, now let's go from B to C. How much do I drop? How much load is present right here from B to C? $60 down, exactly right. So if I'm at negative 70 and I go 60 down, that's going to put me where over here? What's that point? Negative 130. Okay. And then again, constant load, linear shear. So let's see if I can do better than that. I'm going to scroll down a bit, see if I can draw a little bit of a straight line better. That's about the best you're going to get out of me. Okay. Now, I'm at negative 130. Then what do? What do I see? Well, I look at the shear diagram and I have a vertical load going upward. A vertical load going upward that's positive 190. So if I'm at negative 130 and I jump up 190, that would put me at 60. And so that's going to be like that. So this is positive 60. Here, I actually don't need the positive because I have that. Now, what does the shear diagram look like from C to D? Somebody tell me in the chat or with your microphone, whatever. From C to D, what does the shear diagram look like? Zero slope, exactly right. So a flat horizontal line. So, and then I'm at 60, and then I drop down 60, puts me back at 0. So, right off the bat, does my reaction force, set of reaction forces, does it satisfy equilibrium in regards to verticals? Yes, it does. The sum of forces in the y direction equals 0 because I started at 0 and I ended at 0. So right off the bat, there you go. Now, that right there, that's the shear diagram. Now, before we move on and start doing something with it, any questions? Okay. Now, in order to draw the moment diagram, I need to integrate the shear diagram. And so integrating means finding the area under the curve. So what I'm going to do is I'm going to set this up in 4 regions. We're going to say that this triangle here, we'll say this is region 1. We'll say this triangle here, that's region 2. This blob trapezoid thing over here is region 3, and we'll talk about a simple way of computing that area here in a second. And this is region 4. Okay. Now, in order to determine the areas, we're going to need to know some dimensions. And specifically, I'm talking about region 1 and region 2, because these are triangles. Okay. In order to determine the area of that triangle, I need to know this dimension. And same thing here. I need to know this dimension in order to determine the area of that triangle. But it's really, really easy. Okay. First off, what is the slope of this line? And you don't need to do any math to figure it out. There's no math necessary to figure out the slope of that line.
Negative 1/3.
Not negative 1/3, negative 3. See, remember, the slope of the shear diagram comes from the load diagram. This right here, that's the slope.
Oh, my bad.
Yeah, no, I see where you were doing there. You're getting the rise and run backwards. But yeah, there's no thing that you need to do there. See, right here, this right here has a slope of -3 kips per foot. This has a slope of 0. And again, because you look at the load diagram, we have a load here, so we get a slope, a load here, so we get a slope, no load here, no slope. Make sense? So I propose that if we call this x1 and call this x2, that we can determine x1 as 80 kips divided by 3 kips per foot, and x2 as 40 kips over 3 kips per foot. And help me out. Tell me what x1 is and what x2 is. Somebody, x1 first. 26.67 feet. You're exactly right. So this is 26.67 26.67 feet. So I'll put that here, 26.67 feet. What about x2? 13.33, exactly right. So 13.33 feet. Now, what do you get when you add up x1 and x2? You get the big 40. You get 40. So that makes sense from a proportion standpoint as well. So now we can start computing areas, okay? And so I'm going to scroll down a little bit just so I got a little bit more room. Let me draw these down a little bit. All right. So how do we compute the area of that first region? Well, it's a triangle, right? So it's 1/2 times the base, 26.67, times the height. What about area 2? 1/2, and that's negative, 1/2 times 13.33 feet times the height. All right, so somebody help me out with the first area and the second area. What do we get for area 1? .67, yeah. So 1066.67, and that's foot kips. What about this one right here, this A2? A2, negative 266. Foot kips, exactly right. Okay. All right, so that's area 1, area 2. Let's skip a bit. Let's skip area 3. How do we do area 4? Area 4 is pretty simple. What is that? That's just, let's scroll up a bit. That's just what, 60 times 20? That's easy, right? Okay. Now this area number 3, okay, so let me sort of draw this over to the side. I'm going to do this down here just to get it out of the way. So let's look at area number 3. I'll show you a little shortcut. Okay, so this dimension here is 20 feet, and this dimension is 70 kips, and this dimension is 130 kips. Now, you could do this one of two ways, okay? You could split this up as like a rectangle and a triangle and calculate each one separately, but here's a really simple way of doing it. What you can do is you can split the difference between 70 and 130 and compute the average. Oop, hold on. And so you could split the difference, and you could say that this triangle right here actually belongs right there. And so what you can do is just average 70 and 130 and multiply it by 20, and that'll give you the answer. But you can do it however you want. So if you take 70 plus 130 over 2 and then multiply that by 20, that works. Okay, did I do that too fast? Does that make sense? Just the area of a trapezoid? You're right. And that comes out and it's minus 2,000. Now, does anybody have any questions before we move on? While we're at it, let's do this. Somebody add up all the positive areas and add up all the negative areas. So adding up the positive areas, you get, let's see, you get A1 and A4. And that's going to be what? 2266.67. And then A2 plus A3, negative 2266.67. So we got the same positive area that we do negative area. So that's a check that what we're doing is correct. Okay. Now, let's do the moment diagram. So here's our horizontal line. Oh, I can do better now. All right, so I'm actually going to put the label over here because I'm running out of room there on the right. Okay, same story, okay? We start at 0, end at 0. So start at 0. Okay, now we're going to take this slowly and make sure that we're clear on this, okay? So we've got 4 regions. So 4 regions means we've got 4 different components of the shear diagram that we've got to draw. Now let's start off with region 1. Now region 1 doesn't go all the way over to B, right? Remember, this is like point A, B, C, and D. Region 1 doesn't go all the way over to point B. Region 1 actually kind of stops like right there. Okay, so I'm actually going to put another guideline down. I drew that down all along. Now from A to this first point here, we go up. And how much do we go up? We go up that area 1066.67. Okay. All right. Now let's talk about shape. Okay. First off, we have a linear shear diagram in this region. This is a line, this region up here. Okay. So if we have a line up here, this has got to be curved. Okay. It's got to be a parabola. It's got to be have a curve to it. Okay. So here's my question. Is it option 1 or option 2? Actually, let me see if I can draw that a little better. Let me scroll down. Is it option 1 or option 2? So which is it, 1 or 2? I'm asking chat. Help me out. Which is it, option 1 or option 2? Does it curve up like 1 or like 2? Okay, we have a lot of votes for 2. We have 1 vote for 1. Mr. Romans and Mr. Ball, you are correct. It is option 1. Okay, and let me show you why. Okay. Okay, watch this. All right. Let's go up to the shear diagram. So always make sure that you're paying attention up here. Okay, right here. So right, at this point right here, we have high, what is going on? Why is that erasing? High shear. Okay. Here, low shear. Okay. So whenever you're drawing your shear diagram, the values on the shear diagram represent the slopes down below. So at the very, very beginning of the beam, at point A, we have a really, really high slope. And then as we go to the right, the slope is going to get smaller until we get to right here where we have zero shear. Zero shear means zero slope. Let's go back to Calculus 1, okay? Do you remember in Calculus 1, one of the things that you always try and figure out is when you're plotting a curve, what is the maximum point on that curve, right? And how do you do that? The maximum point on a curve, or the maximum or the minimum, the extrema, is where the derivative equals 0, right? Because as the derivative equals 0, right, that's where you're going to get that peak, okay? Well, I propose that the shear diagram is the derivative of the moment diagram. And at this point, right here, we have zero shear. So zero shear has got to be zero slope. So this shape wouldn't work, because if I were to draw it like that, I would have zero slope at A, and I'd have a lot of slope there in the middle. Okay, does that make sense for those of you that answered 2? Is that clear? So again, no. Oh, okay. I'm sorry. I probably wasn't writing it very clearly. I'm sorry. That's probably more on me. So the moment diagram is going to look like this. Going to look like that until when we get to 10.6.67, the slope is 0. Okay. So here, let me. Oh, God bless it. I didn't mean to do that. Okay. All right. Let's chug along. Let's see what happens when we go past this. Okay. What about from this point to B? Okay. Well, how far do we go down? If we're at 1066.67, where should we be on the other side? Well, first off, we should go down, right? We should be going down because the area is negative. It's going to be at 800. You're exactly right. Because we're at 1066.67 and we drop A2, okay? We drop A2, and A2 is negative 266.67. So if I'm at 10.67 and I drop down 266.87, that puts me at 800. Now help me out with this. Let's try this again. That's option 1. Oh, my pen doesn't like me right now. I don't know why. This is option 2. Is it 1 or 2? Okay, we got 1 vote for 1. Got another vote for 1.
I'm also.
I want y'all to be confident in your answers. You're in the 1 camp. You're exactly right. Everybody who's saying 1, you all are right. It's going to drop down because 0 shear, and then the value gets larger, so the slope gets larger. So we go down like that. Okay. Now, what happens from B to C? Well, first off, from B to C, we have a lot of negative area. So we're going to be dropping down. How much are we going to drop down? Like if we're at 800, at point C, what are we going to be at? Negative 1200. That's right, because our area is minus 2000, right? Because again, you look at your areas. This is plus, I don't know what's going on with my charger or my pen here, but it's like wanting to erase. So this is, I'll worry about that part later. All right, so 1066.67 and 800. So we're going to drop down minus 2000 because that's what we get right here. That's our area. So we're going to do negative 1200. So this is going to be minus 1200. I don't know why it's doing that. It's like it's wanting to erase my lines. I don't know what's going on there. Okay. And then again, it's going to go from a little to a lot, a little slope to a lot of slope. So it's going to do, here, I'm going to scroll down a bit so I can draw this easily. It's going to do that. All right. In other words, it's going to do this and not that. It's not going to do that. Okay. Now, the last thing is what happens between C and D. I'm at negative 1200, and I'm going to jump up 1200 to 0. So I am going to get back to 0. What's that going to look like? It's going to look like a straight line, because all the other regions in the shear diagram, Mr. Romans is exactly right. All of the other regions in the shear diagram are linear, so we get parabolas on the moment diagram. But between C and D, we have a constant shear diagram. So a constant shear diagram means linear moment. This is a line. And so this is where like having a straight edge helps, because when you're drawing it out, you can tell when you drew a line on a straight edge and when you just drew a curve. So maybe I'll put here linear. So that's a line. And that's your moment diagram. So here's your shear diagram, and that's your moment diagram. All right, let's take a sec. I want to see if anybody has any questions. Is everybody comfortable with the way that you construct it? You know, like if I was looking here on the board, lot to a little, so it would go up like that, little to a lot, it would go down like that. I want to make sure that this makes sense. Any questions on this? Let me look here at the chat, make sure I didn't miss anything. Can we get an example of concave up? We probably are going to have one soon, like down the line. One of the like best examples of that is moment diagrams for cantilevers, because you end up like the way that it works is you on the fixed end you have a lot of moment, and then on the free end you have like no moment, and so when you draw it, it does kind of concave up. So cantilever beams are a very good example of that, but I want to hold off discussing cantilever beams. We're going to talk about that next Monday. The reason why is because one of the, like I said, I'm taking each load one at a time. And so on Friday, we're going to talk about triangular loads and how the graphical approach really doesn't work. Monday, we're going to talk about concentrated moments, like a 20-foot kip moment. And so that's the deal with a cantilever beam, is you got that moment reaction on the fixed end. So we are going to have a concave up example when we do cantilever beams. That's a great question. And to further respond to that, that is the most real world example of what you're talking about. Because here, I'll show it to you on the whiteboard super quick. So just to give you an idea, and like I said, we'll learn how to construct these things later. But when you look at a moment diagram for a cantilever beam, so let's say here's the cantilever beam, and you have, let's say, a distributed load. What happens is your shear diagram, it actually, you jump up, and then it goes down like that, so it's like a triangle. But then your moment diagram, what it does is it jumps down, and then it does that. Okay, so that's your diagram, and that's your moment diagram. But there's some things here that probably don't make a lot of sense. Like, for instance, you can look at this, and you can see that all the area is positive. So there's no negative area. So you're like, well, that doesn't make sense. Like, it has to equal 0. So how come it doesn't? And that's where concentrated moments and that aspect come into play. So that's why I want to spend Monday and just talk about that, because that's sort of the deal with the concentrated moment, is that when you look at the shear diagram, your positive and negative areas won't match because of those concentrated moments. And so how do you deal with that? That's going to be the story for Monday. That's a really great question. Any other questions? All right, well, I got you a couple practice problems on this on Friday, due Friday. Hey, one other thing. On Friday, we are going to do the pesky triangular load. And the triangular load really doesn't work using these graphical approaches. There are some ways you can get around it. But one of the things I want to introduce is Excel, Microsoft Excel. So we're going to be using spreadsheets on Friday. So make sure that you follow along with that. So so we'll be breaking out spreadsheets. That's all I have, everybody. I will see you all on Friday. We'll break out some Excel. That's all I got.